So now we have seen one property, that is quantization of charges. Charge on a body must be always an integral multiple of the basic charge, that is Q is equal to NE. It should be an integer, N should be equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. Now, who discovered this? That it should be in the form of quantized, that the number of charges, electrons removed or transferred from one body to another should be in the form of integer. That is Michael Faraday. Faraday said, or he told that charges are always quantized. They should be in the form of integers. And this is only a theory, he said. And he didn't prove it. And experimentally, it was proved by Millikan. Millikan experimentally proved that charges are quantized. So this may be a one mark question. Who said or who proposed that the charges are quantized? It is Michael Faraday. And who proved experimentally? It is Millikan. Now there is one more scientist who comes in, whose name appears in static charges, that is Coulomb. Coulomb gave a mathematical expression for the force between the charges. We write the properties: like charges repel, unlike charges attract. And with what force? How do they, and what is the amount of force? On what factors does it depend? All these factors are very important. So that is called Coulomb's law, and very important concept for your knowledge as well as for the exam. So Coulomb, you see the spelling C-O-U-L-O-M-B. We say it as Coulomb. So Coulomb's law. Inverse square law actually it is. As if we have Newton's law of gravitation. Very similar to Newton's law of gravitation. Now if you just remember that first year part, Newton's law of gravitation says that every body which is having mass, every body attracts every other body, because gravitational force is only attraction with a force, and that force depends on the masses. If you take more masses, definitely the force will be more. And it is inversely proportional to square of the distance. That means if you keep the masses far away, the force decreases. It is decreasing inversely as the square of the distance, not simply as the distance, square of the distance, inversely proportional to square of the distance. Similarly, I will take two charges. I will take a sphere, I will rub it, or I will, by conduction, by some means I charge it. I will take a point charge. Sir, what do you mean by point charge? Point charge is one whose size is small, but charge may not be small. Charge may be very large. So its size is very small. So take one point charge, take another point charge, Q2. Let they be separated by a distance r. I will take it in a simple way now. Let they be r be the distance between them. What is the amount of force between them? Let they be positive, both be positive, plus, plus. You can take any type of charge, plus, minus, plus, plus, minus, minus. For simplicity, we will take plus both. So one body is charged positively, somebody might have removed electrons. And from this body also somebody might have removed electrons. I name them as A and B, body A and body B. So both are positively charged, but not by equal amount, different amount, Q1 and Q2. Q is the symbol used for representing a charge, and they are separated by a distance r. Now in your knowledge, as your knowledge goes, how do you think? The force between them, repulsion between them, depends on what factors? It is a natural phenomenon you can think of. Definitely that depends on the amount of charge. Suppose you had kept stronger charges in the same places, definitely they might have repelled with more force. Suppose if you have kept some smaller amount of charges in the same place, in the same distance, they might have repelled with the weaker force. That means force between the 2 point charges must be directly proportional to the amount of charges, whether it is attractive force or repulsive force. Let us not bother about it. Whether they are positive charges or negative charges, let us not bother about it. Let us write only the product of the charges, magnitude of the charges, product of magnitude of the charges. So this is the statement given by Coulomb, the same scientist. He said, force between 2 point charges, electric force, I am not talking about gravitational force or nuclear force. Electric force between 2 point charges is directly proportional to the product of magnitude of charges. Okay? If you take stronger charges, definitely the force should be more. If you take weak charges, definitely the force will be less. I am not writing vector here. I am interested in what is the amount of force. Direction we will take it later. What about the distance? Will it decide the force? Definitely. As you keep them far away and far away, force becomes weaker and weaker. As you bring them closer and closer, and this holds good in even magnets. in gravity. If you bring the magnet very close to another magnet, definitely the force of attraction or repulsion will be more. And he says it is inversely proportional to square of the distance between them. It is inverse square law. So if you are asked in the exam, state Coulomb's inverse square law or Coulomb's law. Coulomb's law states that the electric force or electrostatic force between 2 point charges and kept in air, that's one thing you have to remember, and let the medium between them be air, because in syllabus we have only to define in air. Okay, you can keep the charges even in some other medium. You can fill this with the glass, you can fill this gap with the plastic or wood, anything, but now we will take it as air. So electrostatic force between 2 point charges separated by a distance r kept in air is directly proportional to the product of magnitude of charges. Each word is important. If you don't write any one word which is a key word in the definition, you will lose the mark, right? So electrostatic force between 2 point charges kept in air is directly proportional to product of magnitude of charges, and it is inversely proportional to square of the distance between the charges. Sir, I have written everything, sir. I didn't write inversely proportional to square. I didn't write it, sir. Inversely proportional. How much mark I will get? 0. Because in such statements, in laws, statements, everything should be very particular. Of course, when you write an explanation for derivation, no problem. If you go wrong some sentences, there is no much seriousness in that. But here it should be very proper. So we are defining a law now. So force, electrostatic force between 2 point charges separated by a distance r in air is directly proportional to the product of magnitude of charges and inversely proportional to square of the distance between the charges. Now usually, you know, once you write the formula like this, how do you write F equal to? I take the magnitude only. If you want to write F equal to, you have to take a constant of proportionality. You know, kinetic energy is equal to half mv square. What is that half? Half is the constant of proportionality. We have F equal to ma. We don't have any constant of proportionality. Of course, that is 1. F equal to 1 ma. So similarly here, we have a constant of proportionality. I put it as k q1 magnitude q2 by r squared. I never bother about plus or minus. That comes when I take the vectors. Okay. K is a constant called, it's a constant, and it's a constant of proportionality. Now, another factor comes into picture. Sir, you said that it is kept in air. Can you define this force when it is not air, something else, glass or plastic, in between medium is something else? No. That means force between the two charges depends on the magnitude of charges, depends on the distance between the charges, and also on the medium. So where is the medium, sir? Nothing is told about the medium. Of course, we have kept the medium constant air, but something has to come in this value, that constant value. So if you want to write F is equal to k, and that k is nothing but 1 by 4 pi epsilon naught. So I will write k is equal to 1 by 4 pi epsilon naught. So this is a new constant or new word that you get. This is a Greek word, epsilon naught. So epsilon is a common word, epsilon naught, that is for air. I'll tell you what is, and this is spelled as epsilon. So right, you have to say that 3 or 4 times in your house, epsilon, and this is epsilon naught. Let me see what is that. So value of k is 1 by 4 pi epsilon naught, magnitude of q1, magnitude of q2 by r squared. This is the formula for the force between two charges separated by a distance, and it is the electrostatic force. Now, what is epsilon naught? Now just we have seen that when you keep two charges and separated by a distance, if you keep on changing the medium, take the same charges, don't change them, keep them in the same distance, but in different media. Keep air once, air or vacuum doesn't make much difference. The force between two charges kept in air and kept in vacuum makes a very small difference. So you can treat them in the same state. So if they are separated by a distance in air or vacuum or free space, then keep them, give the same two charges separated by the same distance in a medium like plastic or glass, then the force changes, and when the media is changed, the force changes. That means there should be some criteria of the medium which decides the force, and that is called permittivity. And this constant epsilon naught is called permittivity of air. or permittivity of free space, I write, or I will replace this R with free space. I will make it common, okay? And even if it is R, no problem. So it is permittivity of free space. It is named as permittivity. You see, in this word itself, there is something given. Permittivity, what do you mean by permittivity? If you place two charges separated by R, then R says, through me you just repel or attract. It gives order to the charges. I am in between, R is in between. Through me you repel or attract. And if the charges are kept in between, if the charges are kept separated by glass, glass says, through me attract and repel. What you will do? And that gives that medium gives the permission for the charges to get attracted or repelled. You can just have an analogy like this. That medium should permit these charges to attract or repel. And how much permission is given by the medium? And that is given by this value, permittivity of free space. And you know that if the medium is something else, you should not put 0 here or epsilon naught. If it is something else, you call it as epsilon, and epsilon is the permittivity of any medium. But for air or free space or vacuum, we give a separate standard, and we say that it is epsilon naught. As if we say velocity of light in glass, velocity of light in water, but velocity of light in air, it is given a separate symbol, C, velocity of light in air. Similarly here, so epsilon naught is the permittivity of free space, epsilon is the permittivity of any medium. And what is the value, sir? I rub this one because we are concentrating on free space. Value of epsilon naught is, it has a value, you have to remember this value. Of course, you need not remember permittivity of all the media. For air or free space, you have to remember. Epsilon naught is 8.854 into 10 to the power minus 12. Sir, this constant for air or free space, does it have any unit? Definitely it has unit. So, unit, how to write the units, sir? You need not by heart it. Of course, you should not by heart. Don't by heart the units. Just remember them from the formula. You want unit for epsilon, right? Permittivity of free space. And how much permission is given by the medium for the charges to attract or repel. How to name it using a unit? You take epsilon from here, F to here. Then you will get an equation for epsilon naught, and from there you can get the unit. So if I write epsilon naught is equal to, what I will get? 1 by 4 pi F, 1 by 4 pi F, and magnitude of Q1, Q2 by R squared. Now write the unit. Now it is very easy to write the unit. Here you have 1 by 4 pi, no unit. Newton comes in the denominator. So Newton to the power minus 1, and distance comes in the denominator. Meter to the power minus 2, meter square comes to the numerator. Coulomb square. This is in the numerator only. So this is the unit. Don't by heart it. Simply remember Coulomb's law formula, mathematical form, and then write the unit. Replace F and epsilon naught, you will get the unit. And even in your brain only, you can just think of, and you can do this, mentally you can do it. Take epsilon naught here, F here, Newton to the power minus 1, meters to the power minus 2, and Coulomb square. That is the value of epsilon naught, and this value you have to remember every time. It will not be given in the exam. 8.854 into 10 to the power minus 12. And one more thing is, sir, suppose you do all the experiments in air. What about this value, 1 by 4 pi epsilon naught? All the things are constants. If you select always air as a medium, then can't you reduce this to a single value? Possible. It is possible. 1 by 4 pi epsilon naught. You can check it using the calculator. Substitute 4, substitute 3.14 here. Epsilon naught has this value. Then for all the SI system units, if you put, and all these are SI system, Newton, meter, Coulomb, all, then you will get 9 into 10 to the power 9. This also you have to remember. So totally 1 by 4 pi epsilon naught gives the value 9 into 10 to the power 9. Okay. Now, suppose you are asked, what type of way it will be asked in the exam. Very important question. State and explain Coulomb's inverse square law. 3 marks, not 1 or 2. State and explain Coulomb's inverse square law. First statement. Of course, I don't write the statement because you will get it in all the books. 1. Statement. What is the statement? A small diagram, if needed, you can draw that. 2 charges, Q1, Q2, separated by a small distance R, and you need not write that it is free space here. It is understood like this. statement. Force, electrostatic force. It should mention what type of force. I'm not discussing about gravitational force now. Electrostatic force between 2 point charges separated by a distance is directly proportional to the product of magnitude of charges and inversely proportional to square of the distance between the charges. And of course, you have to add one more sentence, and it takes it applies in the direction of force, or it acts along the line joining the charges. Of course, that sentence you have to add. For electrostatic force between the 2 point charges separated by a certain distance is directly proportional to the product of magnitude of charges and inversely proportional to the square of the distance between the charges, and it acts along the line joining the charges. And that is one more sentence you have to add. It acts along the line joining the charges. We will concentrate on it when you write the vector form of this. So that is the statement. And explanation. Consider two charges separated by a certain distance r. F is directly proportional to the product of magnitude of charges and inversely proportional to the square of the distance, and all these things. F is equal to a constant of proportionality, and the formula here, and K is a constant given by 1 by 4 pi epsilon naught, and epsilon naught is called permittivity of free space, and substituting this we get this formula F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is the mathematical form, not in vector form now. Vector form you have to write it. And what is epsilon naught? Permittivity of free space, value of epsilon naught is this one. Write the unit, that gives you 3 marks. Very small package with high marks. And there is no chance of going wrong and all, because all these things directly proportional, inverse proportional, you have studied it in the Newton's law of gravitation. So you can use the same idea here also. So Coulomb gave you that law. So we were able to find out the force between the charges. Now the question is, I'll rub this, I'll retain only formula. Now the question is, who will be repelling whom? How do they repel? It is just like Newton's third law. Now suppose this is 100 Coulomb, say plus. This is plus 1 Coulomb. One is very weak and another is very strong. Now will 100 Coulomb repel 1 Coulomb with some force, and will 1 Coulomb with the will 1 Coulomb repel 100 Coulomb with the same force? Exactly, correct. They will repel with equal and opposite force. So now we have to write the direction of force. How to write the direction of force? Now Q2. Q2 is repelled by Q1. What Q2 will do? Q2 will repel Q1 also. So Q1 experiences force from Q2, and how it will be? You imagine that on whom you are applying the force, keep that charge in your pocket. That is the best way. Keep Q2 on your pocket and stand here. So you are here now. Of course, you have to stand here. This is the point you are standing. And you stand here and hold Q2 in your pocket, or hold it like this. What happens? You will feel that Q1 is pushing you away. Both are positively charged, and you are simple 1 Coulomb in your pocket now. 100 Coulomb is pushing you away. So I write the direction like this, and I write this as force on to. Always you have to write that number on which force is acting and who is exerting by 1. Force acting on 2 and exerted by 1. Suppose your mother is suppose your mother today beats you in a stick, and if your neighbor uncle looks into all these incidents, you are beaten like anything, and you cry, and your neighbor uncle watches all these things, and he comes to you and asks, how is the beatings and how did you feel it? He has to ask you, not the mother. You have experienced it, and one who has experienced it will know how stronger is the force. So now the force exerted by 1 on 2 is experienced by 2. So who is experiencing it? 2, that first. And who is giving that force? That is next. You don't go and ask, uncle won't go and ask mother, how was the beatings? You have to ask, the uncle has to ask you, because you have felt it, you have enjoyed it. That's why uncle will ask you, how was the situation and how did you feel it? So similarly here, force on 2 by 1, because you are holding 2. And this force is like this. Let me give the vector form like this. F on 2 due to 1. Now leave this 2. Now come to the place of 1, hold it. Now ask 1, charge 1, Q1 and Q1. You ask Q1, how are you? How do you feel the force? Okay, Q1 says, please hold me, you will come to know how is the force. Come and hold Q1 and keep it in your pocket. Now you feel that that Q1 in your hands is pushed by Q2 to this side. Is it so? I hope you can follow this, right? So Q1 is pushed on the other side by Q2. Q2 repels Q1 on this side. So force experienced by 1 and exerted by 2, I have to write it like this. Force on 1 by 2, it is like this. I write the vector form. So they are in opposite directions, you see here. So Q1 exerts a force on to Q2, which is like this, and Q2 exerts a force on Q1, is like this. And who is experiencing? Write it first. Experienced by 1 and exerted by 2. Experienced by 2 and exerted by 1. So shall I write F12 is equal to F21? Definitely I can write it, because I have not taken it as vectors. I have taken it as only magnitude. So magnitude wise they must be equal. But if I want to write the vectors, they are opposite vectors, so I have to put a negative sign. This is exactly the Newton's third law, that is action and reaction are equal and opposite and they act on different bodies. So if you take this as action, on the contrary, Q2 repels Q1 and you can take it as reaction. Whereas if you concentrate on Q1, Q1 puts a force on, Q2 puts a force on Q1, and on the contrary, Q1 puts a force on Q2. If you kick a wall, you are applying a force on the wall. Wall gives an equal and opposite force on you. So they are equal always. So remember, if you are using the Coulomb's inverse square law formula, F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Epsilon naught is called permittivity, R is the distance between the charges, and Q1 Q2 are the magnitude of the charges now. Now, if you are going to calculate what is the force exerted by, exerted on 2 by 1 like this, you have to write Q1 Q2, that means 1 into 100. What is the force exerted on 1 by 2? 2 will push it like this, and you have to write 100 into 1. Answer is same. So whether you write Q1 into Q2 or Q2 into Q1, answer is the same. So it's very surprising that even this is 1 Coulomb, even this is 100 Coulomb. 100 Coulomb pushes 1 Coulomb with some force, and with the same force 1 Coulomb pushes the 100 Coulomb in the opposite direction. This may be a competitive entrance exam question. Two charges 100 Coulomb and 1 Coulomb are separated by a small distance. What is the ratio of force exerted by one on other and each other? What is the ratio? Force exerted by 1 Coulomb on 100 and force exerted by 100 and 1. 100 on 1. What is the ratio of them? 1:1. That's all. Because there is no difference in the force. The product is same. Even if you write Q1 Q2 or Q2 Q1, you get the same answer. But vector wise, if you want to write, it should be equal to minus. But magnitude wise, they are one and the same. So this is the form. Suppose you are asked in the examination, write the mathematical form of Coulomb's inverse square law. 2 marks. This one. And you have to explain the terms if it is for 2 marks. Mathematical form of Coulomb's law is F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where Q1 and Q2 are the charges and this is the magnitude, R is the distance between them, epsilon naught is the permittivity of free space. Okay. What is the vector form of Coulomb's law? Write the Coulomb's law in vector form. Of course, you can write it here. If I can write the formula like this, what is F12? 1 by 4 pi epsilon naught. So I will write F12. Simply F12 is equal 1 by 4 pi epsilon naught Q1 Q2 by R12 square. I will write R12 is the distance from 1 to 2 and R12 cap, because the left hand side is a vector, whereas right hand side there are no vectors. Charge is a scalar quantity, already we have seen the distance is square, and this is a scalar, permittivity is a scalar, it is just a value, it has no direction. This is a vector. This is a vector now, R12 cap. And you have to explain Q1, Q2 distance and everything you can explain. What is R12 cap? R12 cap is a unit vector which is in the direction of force F12. There should be in the same direction. That means it is in this direction, R12 cap. So R12 cap is in this direction. What is F21? If you want to write F21 vector, then it is 1 by 4 pi epsilon naught. Again Q1, Q2 or Q2, Q1, you can replace it, one and the same since it is magnitude only. R21 square into R21 cap. What is R21 cap? R21 cap is a vector in the direction of force F21. So this and this are opposite actually, because R12 cap and R21 cap are equal and opposite. R12 cap is like this, R21 cap is like this, unit vectors. Okay, But in the examination, you can minimize this. You need not write all these things. Write Coulomb's law in vector form. Simply write like this. This is enough. Vector F, same formula, 1 by 4 pi epsilon naught. We will write it in general. Let us not worry about 1, 2 and all. This is for knowledge, this is enough. But for examination, in the paper, what you have to write? Because in the paper, you have to write minimum. And you should know more things. You have to write minimum in the paper. Minimum in the sense, what is required for the question. So, write Coulomb's law in vector form. 1 by 4 pi epsilon naught, Q1, Q2 magnitude, product of the magnitude of the charges, inversely proportional to the square of the distance, and R cap. This is enough. So, write Coulomb's law in vector form. This answer is enough. And but you have to explain the terms where F is the electrostatic force between the charges, Q1 and Q2 are the charges, R is the distance between them, R cap is a unit vector in the direction of force. That is what you have to write. Okay. Now, I am finding duster always missing, but it is here. Okay. Now, another important one. So, this explanation is very important. Of course, this factor you should know it for the examination. For problems, you must know it. But this one you may be asked to write. And Coulomb's law, statement, explanation, everything is very important. Right. Now, another important question that you will get here is the definition of 1 Coulomb. So, if you are asked to write what is a charge, it is a basic property of some elementary particles. Charge is the basic property of elementary particles. And which is the property or which is the criteria that decides the two kinds of charges, that is positive and negative. Okay? Positive and negative are the two kinds of charges. And what is the basic charge that is available, or what is the minimum charge you can transfer from one body to another? That is the charge of an electron. What is the charge of an electron and all? What is the SI unit of charge? Coulomb. C-O-U-L-O-M-B, or 1 C only. Define, this is a usual question, define SI unit of charge. Now, this was a famous question. Usually students commit a mistake here. What is define SI unit of charge? Usually students write SI unit of charge is Coulomb, but they didn't ask you what is the SI unit of charge. They have asked you to define the SI unit of charge. If you write SI unit of charge is Coulomb, you have not defined it. You have to define what is Coulomb. So, SI unit is Coulomb, C-O-U-L-O-M-B. See because when you write some other explanation, if the spellings are going wrong, no problem. But when you are writing answers like this, what is the SI unit of charge? Coulomb, you should not go wrong. So, Coulomb is the SI unit. You have to define it because it is a definition asked. How do you define it? You know that the force between two charges separated by a distance Q1 and Q2 are, then F is given by this equation, Coulomb's inverse square law. Using that law, we can define what is 1 Coulomb. So, you have to make use of this force, and according to your convenience, you change it. What changes we can make, sir? You are going to define what is 1 Coulomb, SI unit of charge, right? So, I will take this one. So, why can't I make some changes here? Let me take this as 1 Coulomb, because however I am going to define 1 Coulomb itself. Let us see what the 1 Coulomb is doing, and accordingly we will define it. For example, if your friend is asking, who is that particular person, and I don't know him, I don't know, please explain him, then what you will do? You will think of that person and what are the specialities in that person, and those specialities you will collect it and you will start explaining. He is like this, he is very tall and he is curly haired, he is white and like this and like that. And you have to take the criteria. Now you have to define 1 Coulomb. Take some criteria of 1 Coulomb. Take this as 1 Coulomb. Why to take this as some other charge? Take this also as 1 Coulomb. Now, keep them separated by a distance of 1 meter. Enough. We will make it very convenient, our very friendly values, 1 meter. Let they be separated by a medium free space, vacuum or air, anything. That doesn't make much difference, very small difference. So, if you do so, how will be the formula? F equal to. So, take two 1 Coulomb charges, keep them separated by a certain distance, 1 meter, not certain distance, 1 meter in free space, and now write the formula. What is the formula? 1 by 4 pi epsilon naught I can write, because I have chosen free space, so I can write epsilon naught if I had chosen some other medium, I should have written epsilon, now it is epsilon naught, into Q1 Q2 by R square. 1 into 1 divided by 1 square, because I have chosen all the convenient values, because we know 1s are table, that becomes very easy. So 1 into 1 by 1 square. What answer you will get here? You know that 1 by 4 pi epsilon naught, last time I have written, if you substitute epsilon naught as 8.854 in 10 to the power minus 12 and use it in your calculator, you will get it as 9 into 10 to the power 9. Just we have seen it. So this is 1 by 4 pi epsilon naught. 9 into 10 to the power 9. We are finding force. You know the SI unit of force, that is Newton, exactly 9 into 10 to the power 9 Newton. Now we have to define 1 Coulomb. By taking 1 coulombs, two 1 Coulomb charges, by keeping them separated by a distance of 1 meter in free space, we were able to get this answer. So why can't you define it like this? 1 Coulomb is that charge, when you place it in front of another 1 Coulomb, but medium should be free space, separated by a distance of 1 meter, then you get an answer of 9 into 10 to the power 9 Newton force between them. So I put it in a beautiful sentence form. 1 Coulomb is that charge, one placed at a distance of 1 meter from another similar charge. That means that should also be 1 Coulomb. So 1 Coulomb is that charge. You are explaining what charge? 1 Coulomb is that charge when placed at a distance of 1 meter from another identical charge or similar charge in free space or vacuum, separated by a distance of 1 meter, and experiences a repulsive force of 9 into 10 to the power 9 Newton. Okay? 1 Coulomb is that charge when placed at a distance of 1 meter from another identical charge in free space, experiences an electric force of repulsion of 9 into 10 to the power 9 Newton. So that is the way we have to define, and it's a very important definition, and all the definition goes in a single sentence, so you have to write it once and you have to study that. And remember, sometimes we forget to write free space. 1 Coulomb is that charge when placed at a distance of 1 meter from another identical charge, because all these ones we will remember, because we know ones are very table very easily. One we will remember, we will forget this one. Suppose this is not free space, then you have to substitute epsilon, which is not 8.854 in 10 to the power minus 12. Answer will not be this one. So it will be different. So we are standardizing it for everything what we get easily. So epsilon free space is available easily. So you can do that. You know the value. So you must be very careful. Sir, if I don't write free space in the exam, everything I have written properly, will I get the mark? No, 0. You must write it. This is an important part. Every word is important. So 1 Coulomb is that charge when placed at a distance of 1 meter from another similar charge in free space. So in the answer book or the book, you underline this, underlining that word in free space. It's very important, because you will come to know that you will forget it every time. So underline it. So when kept at a distance of 1 meter in free space, repels it with a force or experiences an electric force of 9 into 10 to the power 9 Newton. So that is the definition. That definition is very, very important, and and this will be asked along with Coulomb's law. State and explain Coulomb's law, and hence define 1 Coulomb. You have to start from Coulomb's law and statement, formula, and explain what is epsilon naught, permittivity of free space, and then take both the charges 1 Coulomb, separate them by 1 meter, then say that you get this answer, then define it. That may be a 5-mark question, very easy 5-mark question. Okay, so that is about Coulomb's law, very important law which gave the electric force between the two charges. Sir, innega problem. So we will take up 2 problems regarding what the topics I have discussed. Okay, one is a very simple one. How many electrons make 1 Coulomb of charge? You know that charge of a single electron, magnitude wise, if you want to write E, magnitude of charge of electron is 1.602 into 10 to the power minus 19 Coulomb. Coulomb is the SI unit of charge. But this is a very small number, and it is 0.00000, 18 zeros and 1, then 602. So that is 10 to the power minus 19. Suppose you want to go for 1 Coulomb, then you need many, many electrons. That is the question now. How many electrons together will make 1 Coulomb of charge? Automatically you have to go for the quantization of charges, that formula. Q, charge on any body, must be an integral multiple of charge of electron, and numbers should be in integers, and that is the question here. How many electrons, N, make 1 Coulomb of charge? Q is 1. What is the charge of each electron? that we know. And if each mango is weighing 50 grams, how many mangoes are required to make 500 grams? Definitely it is 10, because 50, 50, 50 added 10 times makes 500. Similarly here, Q is equal, N is how much? So if you go on substituting it, Q needed is 1 Coulomb, and N is the question mark. You have to find out N, and charge of each electron is 1.602 into 10 to the power minus 19. Now N is 1 by 1.602 into 10 to the power minus 19, and if you calculate this, you will get it approximately as 0.62 into 10 to the power plus 19. So this comes to the numerator. 1 by 1.6 is almost 0.62, and that is equal to, you can write it as 6.2 into 10 to the power 18. Now what unit will write? There is no unit, this is a number. So many electrons have to be transferred. So if it has to be plus 1 Coulomb, say plus 1 Coulomb, you have to remove so many electrons. So finally you have to write a conclusion here. How many electrons? The question is asked like this: how many electrons make 1 Coulomb of charge? Plus 1 Coulomb. So if a removal of so many electrons, 6.2 into 10 to the power 8 electrons, makes plus 1 Coulomb for a body, and addition of this many electrons makes it minus 1 Coulomb. So simple formula and simple explanation. For 2 marks this may be a question. Okay, that is one. Now this, going to this problem, and this is one basic problem that you get in charges regarding forces, that is the electric force between the two charges. And for this problem, okay, I will read the problem once. 2 positive charges, 4 microcoulomb and 6 microcoulomb, are placed at the corners A and B of an equilateral triangle of side 3 meters. Find the electric intensity at the corner C. Now we will move on to the second problem. 2 positive charges, 4 microcoulomb and 6 microcoulomb, are placed at the corners A and B of an equilateral triangle of side 3 meter. Find the electric force on the charge 1 Coulomb kept at C. Okay? Right. So you have to take 2 charges, and all the charges are point charges. Keep them at the 2 corners of an equilateral triangle, and find out what is the force acting on the third charge, that is 1 Coulomb, kept at the third corner. So you draw an equilateral triangle and name it as A, B, C. You have the freedom to name it anywhere, but for the time being we will follow this. This is how I name. You can name A, B, C anywhere, but keep the charges at the particular places, and we will place 6 microcoulomb and 4 microcoulomb at corner A and B. Okay, 6 here, 6 micro, okay, and 4 micro here. Okay, let this be 4 microcoulomb, let this be 6 microcoulomb. Never mind, you can do it in the other way also. So they are kept, and both are positive. This is plus, this is plus. They are kept at A and B. And at the third corner C, you have to place 1 Coulomb charge. So let me place 1 Coulomb here, plus 1 Coulomb. What is the net force on this electric force? Electrostatic force. If I want to find it out, I must use the parallelogram of law of vector addition. In the first year you have seen, if 2 vectors are acting in the 2 directions and both the vectors are acting at the same point, then the resultant is given by the diagonal of the parallelogram if you are able to put them in the form of a parallelogram. And the resultant given by the diagonal of the parallelogram, when you represent 2 vectors in the sides of the parallelogram, is given by root of a square plus b square plus 2ab cos theta. This is the formula. If 2 vectors A and B are inclined at an angle theta, and if they are acting at the same point O, then the resultant is given by the diagonal of the parallelogram like this. If they can be represented by a parallelogram, R is given by the formula this one. So if I want to write what is the electric force acting on the charge kept at C, first of all I have to write how many forces are experienced by the charge kept at C. Of course, you take 1 Coulomb, put it in your pocket, and yourself experience how many people are pushing you. When you stand here, keep 1 Coulomb in your pocket, that 1 Coulomb will be repelled by this 4 microcoulomb like this. And you know, in Coulomb's inverse square law it says the force acts along the line joining the charges. Line joining 4 micro and 1 micro is this one. So this is force on C force acting on 1 coulomb kept at C on C due to A, F on C due to A. This is one force. At the same time, 6 microcoulomb won't sit quiet, it will also repel you, and the force exerted by 6 microcoulomb on 1 coulomb, it is like this. So force on C due to B. So the two forces you have to decide. So two charges will repel this plus 1 coulomb in two directions. Now what about the fate of this 1 coulomb? Will it go in this direction? Will it go in this direction? No. It will go in the diagonal of the parallelogram direction. So if you were able to complete the diagonal, so represent this by one side of a parallelogram and draw a parallel line here like this, and you can represent this by one side of the parallelogram, draw a parallel line here, then the resultant is given by the diagonal of the parallelogram like this. So that is the force acting on, net force acting on C, Fc, total force acting on C. So if this is equilateral triangle of side 3 meter, you know that it's given here, they are kept on the three sides of, two corners of an equilateral triangle of side 3 meter. This is also 3 meter. Definitely this angle of the equilateral triangle makes 60 degree. Angles of a equilateral triangle are 60 degrees. And these forces act along the line joining the charges like this. So this is a straight line, this is a straight line, and this is vertically opposite to this angle. So this is also 60 degree. So you know theta here now. This theta is 60 degree. Okay, and you can substitute cos 60 here. So, but if you want to substitute what is the first vector, second vector, then you have to find it out. Now the Coulomb force between two charges, you have the formula. Coulomb's force between the two, electric force between the two charges separated by a distance is given by, magnitude wise I will write 1 by 4 pi epsilon naught, permittivity of free space, Q1, Q2, magnitude only, divided by distance square. Okay. Now substitute the values. One by one we will find out. Force on C due to A we will find out. Force on C due to A first. Force on C due to A is equal to 1 by 4 pi epsilon naught. You know that it is 9 into 10 to the power 9 into, okay, Q1, Q2 by distance square. Q1, this is 4 microcoulomb, Q2, 1 coulomb divided by distance square, 3 square. It is in meters only. So for simplicity I have taken all those things, since it is the first problem we are discussing. Then we can go for different types of problems and make it a little bit complicated. Okay, now this is 3 square, 9, 9 and 9 get cancelled. So only the thing remaining here is 10 to the power 9 and this minus 6. So 10 to the power minus 6 and 10 to the power 9, 10 to the power 3. So that comes to force on C due to A is equal to 4 into 10 to the power 3 Newton. And this is along AC. So this is one force. Similarly, find out force on C, this 1 coulomb. They are asking you find out the force on 1 coulomb due to other charges. Remember, 1 also exerts a force on A that is in this direction, but that is not asked. Asked one is what is the net force? Find the electric force on the charge 1 coulomb kept at C. That is what is needed. Okay. So now force on 1 coulomb due to B. So problem, okay. Force on 1 coulomb, force on C due to B is equal to force exerted by B on C. So FCB is equal to this one in this direction. 1 by 4 pi epsilon naught once again, and you know this answer 9 into 10 to the power 9. Q1 that is 6 microcoulomb, Q2 1 coulomb divided by again distance square 3 square. It is meter, so no 10 to the power here. 3 square is 9, this gets cancelled. 10 to the power 9, 10 to the power minus 6, 10 to the power 3. So this is 6 into 10 to the power 3 Newton. Because, and this is along, what is the direction? From B to C, so along BC. So that is the force. I rub this formula because you know it now. Okay. So at the same time, this charge experiences two forces. One in this direction, one in this direction. Finally, how should it move? Suppose you see ants pulling a food particle in different directions, but if you look into the food particle, it is moving in a particular direction. What is that direction? It is the resultant of all the forces exerted by all the ants. Similarly, the resultant of this force is given by the formula. So, net force on C is given by root of A square. A square I will take it as this one. Force on C due to A plus force on C due to B, A square plus B square plus 2AB, 2 force on C due to A, force on C due to B, cos theta. This is the magnitude of force. Now, if you want to see the magnitude of force, that is equal to net force on C, charge kept at C, 1 Coulomb, is root of force on C due to A, that is 4 into 10 to the power 3 whole square, plus C due to B, 6 into 10 to the power 3 whole square, plus 2 into 4 into 10 to the power 3 into 6 into 10 to the power 3, cos 60. You know that it is the opposite side to the one of the angle of the, or vertically opposite angle of the equilateral triangle, cos 60. So, that is equal to, I will rub this. I think you can remember the problem now, since we have discussed it. Yes. Now, what is the force on C is equal to, now here is 10 to the power 3 square, here is 10 to the power 3 square, here is 10 to the power 3, 10 to the power 3 product. So, you have 10 to the power 3 square, 10 to the power 3 square, 10 to the power 3 square, 10 to the power 3 square. You can take 10 to the power 3 square outside the common, but you can take it outside the square root also. Square root of 10 to the power 3 square is 10 to the power 3. So, I can write it as 10 to the power 3 here. Same 10 to the power 3 squares, here 2 10 to the power 3. So, that is also square. Outside the bracket, outside the square root. Then inside the square root, what do you have? Only 4 square, 16, plus you have 6 square, 36, plus then here you have cos 60 is half. So, I will write half here, and this 2 and this 2 will get cancelled. This cos 60 is half, this 2 and this 2AB. So, 2 will get cancelled. Only remaining is 24, 10 to the power 3 square has been taken outside and square root. So, you have 24, 6 4s are. So, what will be this one? Square root of, this is 42 and 52, 56, square root of 76, of course, into 10 to the power 3 you have this one. So, 36, 42, 52, 56, 76. Yes, 76. So, force on C, net force on C is, the answer is, it comes to 8.72 into 10 to the power 3 Newton per Coulomb. You can calculate it using a calculator. This is the answer. Now, suppose the question is to find out the net force on C, the magnitude of force as well as the direction, both. If you are asked to find out both, how to find out the direction? What is the direction of the force experienced by the charge C compared to any other direction? So, I have to take some angle now. Let this resultant force make an angle phi with the FCB. So, this is FC, I will correct this here, FC, resultant force on C, and let phi be the angle made by resultant force with one of the forces. I have not taken this phi with this one. Since I have not taken phi with the angle phi with the FCA, I have taken it with FCB. You have to write the formula like this: tan phi, the angle made by the resultant force with one of the forces, is equal to FCA sin theta divided by FCB plus FCA cos theta. Usually, when you find out the resultant, the sin theta and cos theta will come along with that force along which you have, or with which you have not taken the angle. If you have taken phi with the FCB, then sin theta and cos theta will accompany with this force, not with this force. Suppose you have taken some alpha here, if you have taken some alpha here, then sin theta and cos theta would have accompanied with the FCB. Okay, now tan phi is FCA sin theta divided by FCB plus FCA cos theta. So FCA sin theta divided by FCB plus FCA cos theta. So if you want to find it out, tan phi is equal to FCA sin theta. What is FCA? We have calculated it. 4 into 10 to the power 3 Newton sin 60 divided by FCB. FCB is here we have calculated this one, 6 into 10 to the power 3 plus again FCA cos theta, 4 into 10 to the power 3 cos 60. That is equal to, now here you see 10 to the power 3 is common, you can take it outside. That 10 to the power 3 common and this 10 to the power 3 gets cancelled. So I can write 4 into, so no worries about 10 to the power 3 now, common here outside, cancels with this one. Sin 60 root 3 by 2 divided by, this is 6 plus 4 into cos 60, cos 60 is half. So 4 into half, that is 2, 6 plus 2, 8. So finally this is root 3 by 2, this is 2, root 3 by 4, this is the answer. What is phi? What is the angle made by the resultant? Phi is equal to tan inverse of root 3 by 4. And you can take this value from the log table, and if I want to write the exact value, tan inverse of root 3 you must know 1.732 divided by 4, that is equal to tan inverse of, this will be 0.443 something, approximately I will do it 0.4 and 1 3 times, yes, 433. And if you search for this number in the tan table, you will get it as some 23 degrees, something like that. Answer will be 23 degrees and approximate answer I have written. So phi is almost 23 point 3 degrees or 4 degrees, you will get 23.4. This answer will be exact, fraction will change a little bit. So what do you, finally how to conclude this? So the net force on C, 1 Coulomb, charge kept at C, is this one. What is the final answer we have got? Yes. Here 8.72 into 10 to the power 3 Newton per Coulomb, net force, resultant force, and it acts making an angle of 23.3 degrees with BC produced, or with the FCB you can write. So final resultant force on C is 8.72 into 10 to the power 3 Newton Coulomb, and that force makes an angle of 23.3 degrees or 23.3, okay, 3 degrees with the BC or FCB. That's what you have to write, final answer. So sometimes you may be asked to find out only magnitude, and sometimes you may be asked to find out direction also. So then you will have to go for some complicated problems. This is not a very simple problem, but still you will have to have a knowledge of previous formulas, root of a square plus b square, and as well as this finding the angle of the resultant. Okay.